All right, we looked at one example problem. Let's look at a second example problem to kind of continue to demystify things. Now, here is the problem. This looks a lot complicated than it actually is. It's a really simple problem. Okay, if we follow the steps. Okay, the question is, find the value of IL. Okay, in example 1, we were asked to find the value of VO, the output voltage. Here, we are asked to find the value of current, which are essentially the same. Think about it. If you know VO, then you should be able to apply Ohm's law to calculate IL, because you know the resistance 4K, 4 kilo ohm resistance, right? This guy. So it's a known problem. They're asking the same thing. We want to find out VO first and then get the value of IL from there. Big deal. Now let's see. Again, like I mentioned, this appears like a really complicated problem. It really is a simple problem. Okay, let's start. Okay, fortunately, we now know where to begin, right? There are 4 steps. Let's retrace the exact 4 steps. What's the step 1? Step number 1 is that we want to ensure that there is a negative feedback, confirm there is a negative feedback. And if there is a negative feedback, then you can assume linear region of operation. Okay, so let's see, the output here is tied back to the negative terminal of the operational amplifier. That is negative feedback, right? So we do have a negative feedback configuration, so we can assume linear region. Okay, that's step 1. What is step number 2? Does anybody remember? KCL at Vn, apply KCL at node Vn, right? So where is Vn? Look at this problem. This guy, okay, this node right there, that's Vn, right? That's Vn. And of course, the node down below is Vp. That guy is Vp, right? That's Vp. All right. Second step is to apply KCL at node Vn. So meaning we have to look at the current going in this branch, okay, which is east to west. Then there is a current going in this branch, okay, and then of course there is a current going in this branch. There are 3 branches, IN, and 2 other branches, one going to the left and the other going to north and then eastward direction. Okay, 3 branches. So the current flowing in this branch would be simply Vn minus 5 volts by 10 kilo ohms. Okay. Now the current flowing in the other branch would be the current flowing in let's see, this branch, okay, would be Vn minus Vo over 5 kilo ohms, right? Because the voltage on this node is VO, V output. Okay, and of course there is this other branch which is carrying a current of IN. Okay, let's sum all of those. I'm going to copy this, as a matter of fact, cut it, applying KCL, pasting it over there. Okay, plus the current going in the feedback branch, this guy. Okay, cut this and then paste it here. Okay, get rid of that. Plus the current flowing in the third branch, this guy. Okay, there are 3 branches. We are adding all the branch currents. Okay, let me clean this up a little bit. There you go. Okay, so writing KCL at node Vn, I have 3 branches, and then the sum of those branch currents leaving that node is 0. Okay, that's step number 2. What is step number 3? Step number 3 is apply the voltage and current constraints, or just apply the rules. Rule number 1 is that Vp equals to Vn. Okay. Rule number 2 is Ip equals to In equals to 0. Okay. So if we know the value of Vp, we should be able to plug that in to the equation 1 here. Okay. We can plug that into the equation 1 here and then solve it. So 2 unknowns. There are actually 3 unknowns, but we have a mechanism to find Vn and In so that we can eventually get a value for Vo. Okay, so in order to find Vp, let's analyze this circuit. Okay, that's Vp, right? That's Vp, and there is no current going in. Ip is 0, right? That's the rule. That's the rule of an ideal operational amplifier operating in ideal OpAmp condition. So what we have really is 3 volts. Pay close attention. This 3 volts forms a voltage divider. Okay, is part of a voltage divider between 6 kilo ohms and 3 kilo ohms. So if you have to find the value of Vp, really Vp is going to be 3 volts divided by the total resistance 6K plus 3K. That's the current flowing through that branch. Multiply that by 3 kilo ohms. Okay, multiply that by 3 kilo ohms. Okay, why is that the case? It's a voltage division, voltage divider between 3K and 6K. Okay, so that's the value of Vp. Straightforward. I'm going to copy this, as a matter of fact, cut it and say find Vp by applying a voltage division. Okay, Vp is a voltage divider. How did I get this? I got this by voltage. It's a voltage divider because Ip, the current going in to this terminal, is 0. The current going into this terminal is 0. Okay. it's not a it's not a very recondite topic. It's not rocket science. Pretty straightforward, simple observation. Okay, what does this turn out to be? So Vp comes out to be 3 volts into 3 kilo ohms divided by 9 kilo ohms. So that is going to be 1 volt. Aha! Vp is 1 volt. Very good. Vp is 1 volt, and now what we have is we can go back to my rule 1. Okay, Vp equals to Vn equals to 1 volt. Very good. We have a value for Vn, and by applying rule 2, I have Ip equals to In equals to 0. Okay, so both of these results, look what I'm going to do. I'm going to use them in the equation 1. Okay, use Vp equals to Vn equals to 1 volt and Ip equals to In equals to 0 in the equation 1 here. So what happens? The first thing I'm going to do, and I get a lot of pleasure by doing that, is to make In equals to 0. Now I plug in a value of Vn equals to 1. Okay, so in place of Vn, I'm going to plug in 1 volt minus 5 volts by 10 kilo ohms plus 1 minus Vo by 5 kilo ohms, all of that equals to 0. Simple enough. So there are a bunch of different ways to do that. I'm going to simply follow the one that makes most sense to me. Minus 4 volts by 10 kilo ohms plus 1 minus Vo by 5 kilo ohms equals to 0. Okay, so I'm going to rearrange 1 minus Vo over 5 kilo ohms equals to 4 volts by 10 kilo ohms. So multiply both sides by 5 kilo ohms. So you can see that this divides twice. Okay, so 1 minus, let's see, add a page here. So this is simple straightforward math from here. 1 minus Vo equals to 2 volts. Therefore, Vo equals to negative 1 volt. Okay, Vo equals to negative 1 volt. Okay, now that's not what we wanted to find out. We wanted to find out IL. Okay, IL. What's the value of IL? Okay, but we just found out that Vo equals to what? Negative 1 volt. Okay, negative 1 volt. Now we should be able to apply Ohm's law. V equals to IR. Okay, so in order to find IL, notice that IL times R, the load resistance on the output, that should equal VO, right? So 4 kilo ohms multiplied by the current, the voltage is given by the product of current and the resistance, right? So Let's go down. So we have a value for R, which is 4 kilo ohms. Okay, multiply that by IL, and we just found out the value of VO to be negative 1 volts. Okay, we should get a value for IL equals to negative 1 by 4 kilo, or 0.25 milliamperes, which is the same as 250 microamperes. Easy, isn't it? All we have done is to apply the rules. Okay, let me make this bold. Okay, this is the answer we were after. We wanted to find out the value of IL. How did we do that? Just to recap, even though the circuit looks incredibly complicated, it's pretty straightforward by applying the steps. Step 1 is to confirm we are in negative feedback configuration. Step 2 is applying KCL at node Vn. Okay, these are the same steps that we did in example problem. Okay, step 3 is to apply the rules, the voltage and current constraints. Okay, we apply the ideal OpAmp rules. Then it's just a matter of arithmetic manipulation. Okay, so we'll stop there, and we will continue with 1 or 2 more examples.